So in this tutorial, we'll be creating this animation. It's a simple animation of a square rolling on a curved surface. So the objective is to create this animation in such a way that it seems realistic that this square is actually rolling on the surface in such a way that it takes into consideration the shape of the curve or the surface it's on, and also the shape of the object itself. Okay, so let's get started. So we open up Blender, go to geometry nodes, and then we'll create a new geometry node system. Okay, so the object I used in my example is a square. So if you press Shift and A, let's look for a quadrilateral, and let's connect that. So there's our square. I'm going to press 7 so it can be in top view. And then what we also need is a surface for this square to move on. So I'm going to add a bezier-curve or bezier segment to join these two together. If you have node wrangler enabled, just go to edit, preference, just search for node, activate it, and then to join two geometries together, you can hold in Control and Shift and then right click and drag over the two. So let me just make this square smaller. Let's make it 0.2. Okay, so the first thing we want to do is we want this square to move along the curve here, to follow the path of the curve, basically. To do that, we'll use a sample curve node. Okay, so the sample curve node, it takes information from a curve and it can give you some output. In this example, you can see here, it can give us the position of all the points on the curve. It can give us the tangent and also the normal. I'll explain later what the tangent and the normal is. But for now, we're going to use the position information, and then we'll feed that information into the transformation of the square. So let's add a transform node. Okay, so you can use a transform node, or you can also use a set position node. I'm using the transform geometry node because I want access to the rotation as well, and we'll see later why. So all we have to do is take the position, which will give us the position of the points on the curve, and let's feed it into the translation. And now when we move the slider here, the factor, you will see the square moves along with the curve. Okay, so one thing that needs to be fixed here, let me just minimize this. One thing we need to fix here is you'll see this square, it moves along the curve, but it maintains a constant rotation, or it's facing one direction. What we want is we want the square to face a direction that's relative to the curve it's following. So if it moves upward here, we want it to face upward as well. So we need to dynamically change the rotation of the square. So the way to do it is to use the tangent of the curve. Now, what is the tangent? So a tangent is basically, if you have a curve, right? Let me just use this. If you, let's say for example, you have a circle, right? You have a circle and there's your midpoint, and let's say we have a radius that goes to the circumference, right? If we were to draw a line that's perpendicular to that radius, this is called a tangent. This tangent is basically, you can think of it as the direction of the curve at that specific point. So on this curve, let's say for example we have this point here, and let's say we have a point here, and let's say we have a point here. The tangent to these points will look something like this. So if we had a tangent here, it will be facing that direction, right? While this one here, as you can see, the curve goes downward, so that tangent faces that direction. And then this here, more or less that direction. Okay, so these arrows aren't straight, but you get the idea. And this is useful because this is what we want for our square. We want the square to face in the direction of the curve, right? So we're going to take the tangent information, and then we will use an align rotation to vector node. And what this node does, it takes a vector, because the tangent information is a vector. If you look at the values here, you can see there's three values: the x, y, and z value. It's a vector. So we feed this vector into the align rotation to vector, and then this node will convert the vector into a rotation, and we can plug it into the rotation socket for the transform geometry node. Okay, one more thing we need to do is think about the alignment we want. Do we want the alignment to be according to the x, y, or z axis? In our case, it's an x direction, right? It goes from left to right. It's the x direction. We want the square to face or be rotated relative to the x position of the curve, right? So if you put it to x, and then if we use the slider, you'll see that the square rotates as it goes along the curve. Okay, another thing we want to do now, in some cases, depending on what animation you want to create, you'd want this square to move with the curve, or maybe you'd want to put it on top of the curve, like we did in the animation here. We have a square that's actually on top of it. So to put the square on top of it, what we'll do is we actually need to use the tangent information again. All right. Okay, so how will we use the tangent information? We'll take the tangent, and then we'll connect a vector node or vector math node and set it to cross product. What is the cross product? Now, let's say, for example, you have two vectors, right? Let's say this is vector A and vector B. All right. If you take the cross product of these two vectors, it will give you a third vector. And this third vector would be perpendicular to the previous two vectors, right? So basically what it does, it takes these two curves and gives you some upright position, like lifting something up to stand up straight. And that's why we are using the cross product, right? And then what we will do here in terms of the z, we'll make it -1. Now I'll explain, we'll see, but I'll explain. If you make this 1, this square, it will snap to the bottom of the curve and move below the curve. If it's -1, it moves to the top. Ask me why. I can't really explain that. If you do know why, you can post a comment below. So we'll take this, and then we'll add a scale vector node. So why do we need the scale? The scale is to say, well, we've taken now, let's remove this. So we've taken the tangent to find the cross product, which gives us a position on top or below the curve. But the scale will determine how far up or how far down from the curve the object would be. In our case, if you think about it, let's look at this square here. So if we want to lift up the square such that it's on the curve, what's the distance we want to move it upward? Now you can see the distance would be from the origin of the object to its bottom. In other words, from the middle to the minimum of the object. That's how much we want to lift it upward so that it sits on the curve. So the information we need is we actually need to find the middle, right? And then find the minimum here, and that distance will be the distance that we will lift up the square to sit on top of the curve. So how can we find that information? So if you go to the quadrilateral node, and let's connect it to a attribute stats node. Okay, so this node, as you can see, it gives us several things related to statistics. Now, first of all, we want the range of this object, right? And we want the range, which means the minimum to the maximum. Basically from the bottom to the top. What's this height, right? What's the height from the bottom to the top? And then what we want to do is we'll divide that by 2, because then it will give us half of that distance, which is the distance we're looking for. And we want this range in terms of the y-axis from the bottom to top. We are in the top view, so the vertical alignment would be from the bottom to top would be on the y-axis. So let's specify that the attribute we're looking for is the position in terms of the y-axis. So we'll add a separate xyz, and let's connect the y attribute. And now when we take the range, actually I want you to see these values. Let's connect this quickly to a value to string, and connect this to a string to curve, and let's connect this to the geometry. I'm just going to add some decimals here. So this gives us the range of this square, right? And you can see currently the range is 0.2 meters, which is what we set it to. The height is 0.2. Now you could have said, well, we could have just taken this information here, but you'll see later why we are using the attribute stats instead. Because what if we use another object, and then we'll have to recalculate everything and replug everything again, different sockets to get the different height. But using the attribute statistic node, if we just plug in another object, it will automatically get the information from that node. Anyway, so we can see we have the range, and now let me just move this one way. Let's move it a little to the side. Let's make this smaller. And we can actually group these. Let's group these nodes just to clear up our workspace. Control G, and then this will be kind of like a tool we have to view values we get out of the nodes, right? So let's just call this a view value. Anyway, so we know we can get the range from here, and then we'll divide it by 2, because when you divide it by 2, that's when you get the distance from the bottom to the top, or halfway through to the origin of the object, right? And then we'll take that value. Let's just see if it's 0.1. Yes, it's 0.1. So if the height is 0.2, obviously halfway through would be 0.1. Okay, so we'll take that value and we'll plug it into the scale, because the scale tells us how far up do you want this object to move. And now with that done, now remember, in terms of the position of the square, it's already dictated by this curve, right? The curve moves or gives us the position for the square. And so we want to add this information to this position, right? Because it's fine, the square can move upward and downward as the line dictate or the curve dictates it to go, but we also want to add the height here to it, right? So we'll use a vector math node, a set to add, and then we'll add this height that we calculated to it. As you can see, now the object has moved upward, and now it's attached to the top of the curve. So let's just test it with a slider, and as you can see, it moves along the curve. It sits on top of the curve. So already we have an animation here where you can basically take any shape and then just slide it on a curve. Of course, this will work, doesn't matter how we change the curve. We can actually test that. Oops, wrong one. So let's say the curve was different. Let's say this is the shape we had, and then when you use the slider here for the sample curve, you'll see it will still just move along whatever the curve is, and it will work for any object or any curve we place here, right? Like for example, in fact, let's take Susie. Let me just add here. We'll add a mesh, a monkey, and then let's just scale it down just to test and see if it works for any object. So I'm going to rotate this on the x-axis -90 degrees, so you can look forward to the front view. And then let's spin this geometry node setup, and then let's drag Suzanne into our geometry nodes, set it to relative, and let's plug it in there. As you can see, let me just hide the original one. As you can see here, it doesn't matter what object you place there, it will just do the same thing, right? Which is useful. It will depend on what you're trying to do. Maybe you want a square, maybe you want a monkey. You can just replace the geometry used there. But anyway, let's continue. So far we have the square that's sliding on the curve, but as you've seen in the video I started with, in the animation, we want the object to actually roll along this object. Now let me just clean up the space here. Okay, so we need to make this object roll, right? And of course what we'll use is we will use some transform geometry node, and then of course using the Z value here we can rotate the object. Now as you can see, because we set up the square the way we did, right, even when you rotate it, it actually considers that this square has pointed tips, and the tips will tilt the square upwards when you roll it, right? So we want this rolling animation, and we want this movement to the front or forward movement, we want that to run together, right? Okay, so the question we need to ask is, how many rotations will this square make from the beginning of the curve to the end of the curve, right? Because if we don't have that value correct, then it won't look realistic, right? So how will we know that? How will we know how many rotations on the curve from the start to the bottom? So think of it like this. Let's just imagine we take this square, right, and let's say we cut it at that point there, and we lay this square out straight like a straight line, right? What we're trying to know is that straight line, how many times can it fit into this curve? Because this is what's happening when it's rolling. Basically each side is being laid on the curve. So a full rotation would have all four sides has been on the curve. So what we actually need to find is, what is the length of this curve, right? What is the length of the square? If we get the parameter of the square, let me put it that way, the parameter, because that parameter will tell us how many times we can fit a rotation of the square onto the curve. Okay, to get the length of this, we can use a what can we use? So we can use a sample curve node. Okay, a sample curve node, and then you'll see here on the left side of the sample curve node there's a socket that has value, right? And at the bottom on the right, or sorry, at the top on the right, there's another value socket. This means we can feed it some attribute, right? And then we'll get the output of that attribute for the curve that we connected it to. So what we want is the length or the parameter of that curve, right? So what we'll use is the spline length, and that will give us the length of the parameter or the parameter of the square, right? And what we want to do is, once we have that length, we need to figure out how many times does it fit into this curve, right? So we also need to know how long this curve is, the Bezier segment. So we'll do the same thing here in the sample curve node. We'll add a spline length, and then we'll take that value and divide by the length of the parameter of the square, and that will tell us how many times this square can rotate on this curve. All right. Okay, so one full rotation is equal to 360 degrees, but we know that in Blender by default it works with the radians instead of degrees. So 360 would be equal to 2 times pi. So we'll need to take the number of times it can roll and multiply it by 2 times pi. That's how many rotations it will require for the square to roll on this surface from the beginning to the end of the curve. Okay, so how will we implement this? Okay, so first thing we want to do is just note here, just remember that for us to make the cube or square roll forward, we need this information, the Z rotation, to go backward instead of forward, right? Keep that in mind. So what I'm going to do is, first of all, I'll add a mix node, and I'll explain why. Why am I using a mix node? Well, with a mix node, it's kind of like the mapping node, right? You can map a minimum and a maximum, and then the factor will slide from whatever minimum to whatever maximum you set here. So what we want to do is we want the slide to be from the beginning to the end of, or let's say from the beginning to this end here with the rotation we calculated. But instead of making the end be, we'll plug it into A at the beginning. The reason why is we want this slide to actually be reversing the value or going backward, right? So with that, let's use a combine XYZ node so that we can have access to the Z rotation and then plug this value in here. So if I were to rotate this, as you can see, when I move the slider forward, the square also rotates forward, right? Okay, but we don't want the rotation to happen all on its own. We also want the forward movement to occur with the rotation. So I'll add another mix node, and then I'll plug this into the spline, or sorry, the sample curve factor, right? And let's set this to 1. Why do we set this to 1? Because this slide here, 0 goes to 1, so we don't want to change that. That's why we keep it 0 to 1. And then we'll add another mix node, and we'll add this mix node to each factor of the other 2 mix nodes. Now when we slide here, it does both the rotation and the forward movement at the same time, right? And there we have the information we need, or the animation we need. So if we want to animate this, we can actually use, instead of this mix node, I'll actually use a scene time node. Let's use a scene time node and plug, we can use frames or seconds, doesn't matter. I'll just use frames. Now if you press spacebar, you don't actually see the animation because it's too fast. The animation is too fast, so we need to slow it down. To slow down the animation, we can use a multiply node or a math node set to multiply, and let's take this down to, let's say, 0.01 and see. So now if we play the animation, you can see it's at a speed that we can see if it works correctly, right? Another thing we can do here, let's just consider this animation here. Now it is not really realistic, and I'm talking about if an object moves on a curve like this, we would think that the surface, the way it's set up, will affect the speed at which the object is moving. In our case here, you would imagine that the a square, when it goes down, it will be a little faster than going up here. Like it struggles up the hill, goes slow and slow when it hits the top, and goes down again, it goes faster. So we can actually implement that speed of the information or of the animation by using a float curve. So if we use a float curve, so what does the float curve do? Now I'm sure you've seen some videos on animation. One of the important things when you animate something is to consider ease in and ease out. So you can actually use a float curve to do that. Like a basic ease out would look, if you want something to ease out, you can use a curve shape like this. Let's just look at it. Can you see it starts fast and then it slows down? That's easing out. And then easing in would look something like that. So it starts slow and then it goes faster. Now, what we want to do for our specific case here, we want it to be a little fast at the beginning, and then as it goes up here, slow down when it hits the top, and accelerate again. So we want the beginning to be a little fast. Okay, so there I got the right curve that fits the animation we want here. So it starts off fast, as you can see here. It's a steep upward movement there, and then this is less steep here. This is this position here. All right, so you can see the upward movement is slower, and then when it hits the top, it goes a little faster. And now we have this information or this animation that looks a little more realistic with the float curve that we put there. Okay, that's it for this tutorial. In the second tutorial, we'll complete the rest of the animation. Thanks for watching. If you want to see more of these, don't forget to subscribe and like the video, share, and if you have any questions, you can leave them in the comments below. Any suggestions as well. And thanks for watching.